This lecture is a bit more mathematical. We're going to learn how to calculate the speed of sound. Sounds seem to move very quickly. However, when you are in a thunderstorm, you might have noticed that you see the lightning before you hear the sound of the lightning. This would mean that the speed of light is much faster than the speed of sound. In fact, the speed of light is extremely fast. In a vacuum, it is 3.0 times 10 to the power of 8 meters per second, which is actually the universal speed limit. There's nothing that can be faster than that. The speed of sound is much slower than that, although it is pretty fast as well. You'd also notice this if you see a gun fired at a track meet, for example. You would hear the sound of the gun after you would see the smoke from the gun. So that is another thing that demonstrates that. The equation we can use for the speed of sound, and it's sort of a variable equation. In this case, we're going to use V equals 331 meters per second plus 0.60 meters per second per degree Celsius times T, which is our temperature. And when I say it's a little bit variable, I mean that the 331 meters per second that we have is that's basically our that's sound at a normal atmospheric pressure. But in cases where you would have different types of pressure, the equation would change. That constant would change. In general, though, the 0.60 additional meters per second we have as we increase in temperature, that would still be the same. We can always assume, unless the question states otherwise, that the atmospheric pressure is at a normal state. So we can use this equation, V equals 331 meters per second plus 0.60 meters per second per degree Celsius times T. Or without the units, V equals 331 plus 0.60 times T. So that is the equation. You may want to copy this down. Your V would be given to you in meters per second when you solve this way, and your T has to be in degrees Celsius. The speed of sound in air was first accurately measured in 1738 by members of the French Academy. Cannons were set up on two hills approximately 29 kilometers apart. By measuring the time interval between the flash of the cannon and the boom, the speed of sound was calculated. Two cannons were fired alternately to minimize errors due to the wind and to delay reactions in the observers. From their observations, they deduced that the sound travels at 336 meters per second at 0 degrees Celsius. So let's use the equation to calculate what is the speed of sound if the temperature is 15 degrees Celsius. So we start V equals 331 plus 0.60 T. We substitute 15 in for T. Then we can calculate 331 plus 0.6 times 15. We have a velocity of 340 meters per second. In this case, we already have it in two significant digits, so we can just stop there. This question says, if the speed of sound is measured to be 318 meters per second, what is the air temperature? So with this question, our speed of sound, well, we start with this equation first. And we need to isolate for T. So that means we can move the 331 to the other side and divide by, so V minus 331, divide by 0.60. We are now left with our substitution, which is 318 minus 331 over 0.60, and t would equal, let's calculate it, 318 minus 331 divided by 0.6. We have negative 21.7. We're going to need to write this in 3 significant digits because our velocity was given in 3 significant digits. The next question here says that we have a 200-meter dash along a straight track was timed at 21.1 seconds by a timer located at the finish line who used the flash from the starter's pistol to start the stopwatch. If the air temperature was 30 degrees Celsius, what would the time have been if the timer had started the watch upon the sound of the gun? So if we waited till the sound of the gun, there would be a little bit of a difference. Well, let's first find out what the velocity is. So 331 plus 0.60 t. This here, we can substitute 30 into that and get our v. We then need to compare our v equals dt after that. V equals d over t. And we need to solve for our t. So t equals d over v. If we substitute that in for our v, we have 331 plus 0.60 t, and that works out to 200 over 331 plus 0.60 times 30. So our t gets to be 0.5731. We need to subtract this from the 21.1. So 21.1 minus 0.5731. And I will just, I'm going to multiply this by negative 1. Then add it to 21.1. We're left with 20.53, or rounded to significant digits, we have 2. Looks like 21 seconds. I think I recall seeing the answer having 3 that they have here, so 20.5. But really, there should be 2 significant digits. If that was the case, there should have been stated that the 200 was 3, and the 30 was needed to be 30.0, but it didn't have that. So 20.5 is what's listed here. So the speed of sound in other media is different as well. We've already talked about how sound travels faster in solids, or waves travel faster in solids than they do in gas, and waves travels faster in liquids than they do in gas. This lists the speed of sound in different materials and air at different temperatures. So write this down here. This point also depends on the medium's properties, not just its temperature. The closer the particles of something are together, the faster they would travel. This question says, a vibrating 400 hertz tuning fork is placed in fresh water. The speed of sound in fresh water is at 25 degrees Celsius as 1,493 meters. What is the frequency in hertz and the wavelength in meters when the water is at 25 degrees Celsius? So, for question 4, here we would have to calculate our frequency. We know V equals F lambda. So F equals V over lambda. And actually, sorry, we're not calculating our frequency. Our frequency in hertz in the water at 25 degrees Celsius. It's already given to us that we have this tuning fork. So we just sort of state that for A that we're at 400. The wavelength is what we're more interested in, so I guess we'll rearrange this. So we'll write here F equals 400 hertz. I'm not sure why that question asked that. So V over F, and that wavelength would be 1493 over 400. Turn on our calculator to see what that would be. 1493 over 400. We get 3.73. So I'll write 3.7 meters is our wavelength for this part A. I'll move the calculator out of the way so you can see what I circled there. It says when the sound waves move in air at 25 degrees Celsius. Well, in this case, we would have to use our equation first to find out what our V is. So V equals 331 plus 0.60 T. And rearranging that equation for lambda, the frequency would be the same, of course. So lambda would be this V, 331 plus 0.60 T over the frequency. So lambda is 331 plus 0.60 times 25 divided by 400. Turning on our calculator. 331 plus 0.6 times 25. That's our numerator divided by 400. We have a lambda equaling 0.87 meters for 2 significant digits. And the frequency is still 400. Ernest Mock was an Austrian physician. Ernest Mock was an Austrian physicist who researched sound waves and devised a way to describe air speeds of objects in terms of the speed of sound. The ratio of the airspeed to the local speed of sound is called the Mach number, and it's calculated this way: m equals airspeed of the object divided by the local speed of sound. An aircraft's Mach number is not fixed. It changes depending on the speed of the sound in its vicinity. So an aircraft traveling at a fixed speed from Helsinki to Havana would have different Mach numbers at the two places because of different air temperatures and pressures. In the late 1940s, there was an international tension between the Soviet Union and the United States. Both sides began a weapons race to outdo the other. Consequently, having faster aircraft became very important. At that time, when a pilot tried to fly an airplane near the speed of sound, significant vibrations occurred within the airplane. These vibrations either caused a loss of control or destruction of the aircraft. So it was breaking of this sound barrier was one of the battles of this Cold War between the United States and the Soviet Union. The problem was because the sound waves emitted by the aircraft built up in front of it, as the aircraft approaches the speed of sound, it starts to catch up to those sound waves. As a result, large compressions build up in one area and form multiple shock waves in front of the aircraft. The shock waves have sufficient force to cause an aircraft to fly differently than it might at slower speeds. In fact, the shock waves can damage the aircraft or prevent the pilot from using the controls effectively. So when an aircraft is stopped, we have concentric sound waves around it. As the aircraft is traveling, the sound waves that it produces, it's essentially moving towards those sound waves. So it has a compression of those sound waves. When we reach the speed of sound, all of those sound waves are right at where the aircraft was, and then at supersonic speed, the plane is traveling faster than the sound that it produces. If the pilot cannot control the aircraft, the situation may become life-threatening. Overcoming this challenge is called breaking the sound barrier. Hundreds of test pilots gave their lives in this effort, about one per week in the 1950s. Despite the dangers, test pilots were willing to take chances for the adventure and to further the research. The challenge of breaking the sound barrier led to new designs for aircraft wings. For example, the wings on a propeller plane are perpendicular to the airflow, whereas the wings on modern passenger jets are angled so that airflow over the wings is smoother. In fact, the greater the sweep of the wings, the faster the airplane. In addition, as a propeller plane approaches the speed of sound, the effectiveness of the propeller is reduced by as much as 50%. Thus, a greater force is required to turn them faster. Experiments showed that the increase in performance required a much more powerful engine, which led to the creation of a jet engine. When an aircraft breaks the sound barrier, a shock egg or a vapor cone appears. This is a visible cloud of condensed water that kind of happens around the aircraft. The water is actually found in the moisture in the air. So when the sound barrier is broken, we have this visual image of the water being vaporized. We also would hear a very loud sonic boom, and that is the sound that's associated with breaking the sound barrier.